Hi there, it's Paul with a script designed to illustrate graphically the connection between infinite series and the sequence of partial sums for an infinite series. So let me start with a slowly convergent series where the general term is 1 over n to the 3/2 power. I regard this as slowly convergent because neither the root test nor the ratio test will show that it converges. As usual, I define the series by a function so that conceptually there are infinitely many terms, but I immediately generate the first 100 of them, store it in a vector, pretty much eliminate the margins, and plot the terms. And you see they go quite rapidly to 0. That has to be the case for any convergent series. Now I'm going to compute the partial sums and store those in a vector named svec. And what I do is just set the nth element of svec equal to the sum of the first n terms of the series. I add these to the plot, and type equals s does a staircase display, which is a nice way of illustrating this. Well, it certainly looks as though those partial sums are approaching a limit. Clearly they're increasing, and they seem to be bounded above. But let's check it. Let's sum the first 1,000, 2.549, the first 10,000, 2.592, the first 100,000, 2.60, and so a reasonable guess is that 2.61 is an upper bound for the sequence of partial sums, and the sum of the series is perhaps a little bit less than that. By contrast, let's now look at a series that diverges, and diverges very specifically to plus infinity. All I've done is to change the exponent from 1.5 to 0.9, and when I plot the terms of this series, they go to 0, but they don't seem to go to 0 as fast as in the previous series. Calculating the partial sums will give me much more insight into what's going on. So I do that and add the partial sums to the plot, and you can see what's happening. Those partial sums just keep getting bigger and bigger and bigger. This series diverges to plus infinity, which means that the partial sums eventually exceed any positive number, capital M, that you might choose. However, if we change the signs on half the terms, we will get a series that converges because it's an alternating series. I foolishly called this series C and had the hardest time figuring out why my concatenate function wasn't working anymore. Then I got smart, went back and named it D. Still not a very good name, I agree. So here is the function. It's 1 over n to the 0.9 in magnitude again, but the minus 1 to the n plus first power has the effect of making all the odd-numbered terms positive, all the even-numbered terms negative. And when I plot that, you can see that the odd terms form a decreasing sequence of positive numbers. The even terms form an increasing sequence of negative numbers. And since the magnitudes keep getting smaller and smaller, and since the limit is 0, all the conditions for an alternating series are satisfied. We can calculate the partial sums exactly as we've done before, and when we add them to the plot, you can see exactly what's going on. It's clear that these partial sums are alternating, being a bit above and a bit below the ultimate limit. I haven't a clue what a numerical value might be for this limit. In general, calculating the limit of an infinite series is a very difficult thing and only works in special cases. Now let's move on to the next topic, the root test. The root test gets less press in AP Calculus courses than the ratio test, but it's actually a much more fundamental and much more powerful test. The reason that it's tricky to use is that you have to know that the limit of the nth root of n as n approaches infinity is 1. Otherwise, you can't do calculations, whereas calculations done for the ratio test require more elementary algebra. The key quantity, known as alpha, is the lim sup for the nth root of the nth term. And in this case, the correct statement is alpha is the limit superior. There is no requirement that alpha be the limit, and I'm going to exploit that fact in my example. So I've chosen alpha to be 0.8, and all that's really significant is that alpha is less than 1. So what does it mean if we say that the lim sup for these nth roots is 0.8? Well, one thing it means is that sooner or later these nth roots are going to get less than 0.9, and because we're only talking about a lim sup rather than a limit, these nth roots can be quite a bit less than 0.9. I could, in principle, have used anything bigger than 0.8 as the upper bound here. And now what I'm going to do is generate a series that's going to pass the root test with some randomness built into it. What I'm going to do is, for the nth term, choose some number that is in the range from 0.7 to 0.9, and then raise it to the nth power. Let's generate 100 of these and plot them, and you can see what happens. These terms go to 0 quite quickly. Why? Because the term itself is behaving like the 0.7 to 0.9 power, and then we're raising that to the nth power. And when you take a number less than 1 and raise it to a high power, it gets very small very quickly. Because of the possibility that the nth root can be as small as 0.7, these terms don't go uniformly to 0. They sort of wiggle around. Now I can calculate the partial sums and add them to the plot, and you can see what happens. The terms go to 0 really quite quickly, and the partial sums stabilize in such a way that they'll never get 1 pixel greater than what they are now. So that's convergence, illustrated by the root test. Now let's make a small change in the exponent. I'm going to choose alpha as 1.02, and all that matters is that this is greater than 1. So if the lim sup of the nth root of the nth term is 1.02, that means the nth root has to be greater than 1.01 infinitely many times, because if it weren't, the lim sup would be 1.01 or less. So for the function that fails the root test, I'm going to generate a random number in between 0.7 and 1.01, and then since that's the nth root, I've got to raise it to the nth power. Generate 100 values and plot it, and this is really kind of interesting, isn't it? These terms are not going to 0. A lot of them are pretty small. That's because the random number I picked happened to be less than 1. But every once in a while, we get a random number that's a little bit bigger than 1. And when we raise it to the nth power, we get something quite substantial. So there are going to be occasional big terms, and there are going to be infinitely many occasional big terms. That's basically the proof that if alpha is greater than 1, the root test shows that the series is divergent. We can illustrate this nicely by calculating and displaying the partial sums. There they are. You see these jumps, and you see the farther along you go, the bigger the jumps become. So we have an infinite number of jumps that keep getting bigger. This series diverges like crazy to plus infinity. Finally, let's look at a case where the root test doesn't work because the quantity alpha is equal to 1. And look first at a case where the series diverges, then one where it converges. The series whose terms are 1 over n is known as the harmonic series. And since this time I'm not using any random numbers in the definition of the function, I can make a vector of the first 200 values very straightforwardly, plot them. They go to 0, not super quickly. We can try the root test on this by just saying take this vector and raise it to the 1 over nth power. If I plot that, I get a sequence of numbers that approaches 1 as a limit. We've already proved that the limit of the nth root of n is equal to 1. So the root test is totally useless. Doesn't prove divergence, doesn't prove convergence. Now let's calculate the partial sums and think about them. So here are the partial sums plotted in blue. And the problem with these partial sums is that they don't form a Cauchy sequence. That's quite easy for me to show. I'm going to show it not with a tiny epsilon, but with an epsilon of 1/2. Suppose someone says, oh, for epsilon equals 1/2, n equals 30 is big enough. Well, there's n equals 30. And I'm going to choose as the upper end of my band the value for the 30th element plus epsilon, and you can see that we very quickly rise out of that band. It's easy to find two partial sums beyond the 30th term whose difference is greater than epsilon of 1/2. Using a bigger n accomplishes absolutely nothing. We can do the same thing with n equals 90, and we can express what we've discovered directly in terms of the series. Basically what's going on here is that no matter what n you pick, I can find a finite sum of terms starting with the n plus first term that exceeds my epsilon of 1/2. For example, if I sum terms 31 through 60 inclusive, I get 0.684, which is bigger than 1/2. If you choose n equals 50, I sum the terms from 51 to 100 and get 0.688. If I do it for n equals 80, I get 0.690. And if you've got an eye for numbers, you're probably aware of a famous number that's mighty close to 0.69, namely the natural log of 2. The natural log of 2 is just a little bit larger, and if you take the limit of what we've been doing as n approaches infinity, you'll get the natural log of 2. If you want to convince yourself that that's so, convince yourself that this sum is actually a Riemann sum for an integral whose value is log of 2. It's easy to convert this argument into a formal proof that the harmonic series diverges. A similar but far from identical argument will let us see why if we use 1 over n squared instead of 1 over n, we get a convergent series. So I'm going to start with a sequence that converges to 2 and plot it. And now I'm going to convert that sequence back into an infinite series by taking differences. I'll set the first term equal to 1 and the second term equal to the second term minus the first term of the sequence, and so on. So now I've constructed and plotted an infinite series, and just to check that I've got it right, I will calculate the 60th term of my original sequence and the sum of the first 60 terms of my series. They're the same. Now let's form the series of inverse squares. The general term is 1 over I squared. And I'm going to plot this in red. Now watch carefully what's going to happen. You see the red partially overwrote the blue lines, but in every case my new series is smaller than the original series. I can show this numerically by taking the difference between the two, and notice I never get anything but positive numbers. And that means the series of inverse squares converges by the comparison test, because the series is term for term no greater than a known convergent series. Since the terms are smaller, the partial sums will be smaller. I can work those out and plot them in magenta. And in this case, the sum can actually be calculated. It was worked out back in the 18th century by the great Swiss mathematician Euler. What he figured by an ingenious argument was that the sum of this series is pi squared over 6. If I plot that, you can see it's a plausible limit. And this argument, too, will be easy to convert to a proof.